Hi, this is lecture number 6 in the series of lectures on basic linear algebra. I am going to solve the problems related to lecture number 5. You can find all of these videos in the playlist with the same title, Basic Linear Algebra, on my YouTube channel. In the descriptions below the video, you can also find the links to these notes that right now you see part of it on your display, both as a PDF file and as a GoodNotes file. GoodNotes is the application that I use to create the files. You can find the links to the empty files as well as the files containing my solutions and explanations. Okay, without further ado, let us start solving the problems. Problem A. Let A be a 2 by 3 matrix and let B be a 3 by 2 matrix such that A sub ij's are defined using these relations and B sub ij's are defined using these relations. Determine A times B and B times A. To do this, we have to determine the explicit form of A and B, then simply multiply them in the corresponding order demanded by the problem, yes? So here it is given to us that A is a 2 by 3 matrix. The generic form of such a matrix is A sub 1 1, A sub 1 2, A sub 1 3, A 2 sub 1, A 2 sub A 2 2, and A 2 3. Okay? But if you look here, this tells you that if the row index is smaller than the column index, the entry is defined to be 0. So here the row index is 1, the column index is 2. So this should be 0. The same for this one and for this one. In all of them, the row index is smaller than the column index. Okay, so this means that these three entries are 0. 0 and 0. Okay, but now on the entries that the row index and the j index are equal, I have to use this rule. Okay, so here the row index is 1, the j index is 1, so I write it as 2 times 1 minus 1, which becomes 1. So this entry is equal to 1. Okay, and here as well, the row index and the j index are equal. So again, I have to use the same rule, but this time I is 2, j is also 2, so this becomes 2. So this entry is 2. And finally, for this one, the row index is 2, I is 2, j is 1. So you see that 2 is greater than 1. Again, I have to use this rule, and then I have to write 2 times the I index, which is 2 in this case, minus the j index, which is 1. So the answer becomes 3. Yes? So this is my matrix A in explicit form. And then I will do the same thing for matrix B, but matrix B is given to be a 3 by 2 matrix, so it contains 3 rows and 2 columns. So the generic form of that matrix is this. Yes? And then we have to follow these rules now. This tells you that if you add the row index with the j index, and if that number turns out to be even, the entry is defined to be 0. So here, if I add these two numbers, it becomes 2, which is even number. If I add these two numbers, it becomes 4, which is an even number. If I add these two, it becomes 4 again. It's an even number. So these three entries are actually all equal to 0. So I have a 0 here, a 0 here, and a 0 there. And now the second relation tells you that if you add these two numbers and the number becomes an odd number, keep that odd number as the entry itself. So here, if I add these two, it becomes 3. 3 is odd. So according to this definition, that entry is itself 3. And for the next one, it is also 3. For the next one, it is 5. As simple as that. And then when I have my matrices, the next task is to multiply A by B. So I write A on the left hand side, multiply it to B, which has to be written on the right hand side. Yes? And because I have explained how to multiply these two matrices in the lecture itself, so I don't spend that much time for this simple problem. Yes, so we know that this is a 2 by 3 matrix, this is a 3 by 2 matrix, so these are equal, so the final answer should be a 2 by 2 matrix. Okay, and then what I do, I take this one and multiply it here, write it here, take this one, multiply it here and write it here, and so forth for the other ones. So the answer to the first one is just 0, the answer to the second one is 3, the answer here would be 6, the answer here is 9. So that is the answer of A times B. Similarly, I will also multiply B on the left to A on the right. So I have to write B first this time, 0, 3, 3, 0, 0, 5. And then I multiply it by this matrix 1, 0, 0, 3, 2, 0. The same story, but this time hopefully you realize that this matrix is a 3 by 3 matrix, because this is 3 by 2, this is 2 by 3, so these are eliminated. What is left is 3 by 3. And again the same story, so I will multiply each row of the left hand side matrix by each column on the right hand side matrix, and I will write it on the corresponding entry of this product. So the first entry becomes 9, the second entry becomes 6, the last one here is 0, then I go to the next row, it becomes 3, 0, 0, and then 15, 10, and 0. So these are the answers of this products, A times B and B times A. Problem B. Let X and Y be these two matrices. If Z is a matrix such that Z times X is equal to Y and X times Y times Z is equal to I, determine B. Okay, so here we don't have any information regarding this matrix Z, but we know that Z is supposed to be multiplied by X and the answer is given to be Y. So assume that my matrix Z is an M by N matrix. So this matrix is M by N. This matrix is 2 by 2. And the answer we know that is also 2 by 2. So to be able to multiply Z from the left to X in the first place, I need to have N equal to 2. So N is definitely equal to 2. And the product should be an M by 2 matrix. On the other hand, I know that the product is a 2 by 2 matrix. So it means that M is also 2. So finally, I conclude that my matrix Z is also a 2 by 2 matrix. Okay, except for that, I don't have yet any information regarding the entries of my matrix Z. So this is why let us assume that the entries are simply alpha, beta, gamma, and theta. Okay, now we know that X times Y is equal, Z times X is equal to Y. So what I can do, instead of Z, I just plug alpha, beta, gamma, and theta in, and then I multiply it by X, which is given in the problem itself, and then equate it with the matrix Y, which is minus B over 2, 0, 0, minus B over 2. And then I start multiplying the left-hand side. So these are 2 by 2 matrices. The product is very simple for you by now. So the answer to the first entry is alpha, the next one is minus beta, gamma, and finally minus theta. This is supposed to be equal to the right hand side matrix, which is minus b over 2, 0, 0, minus b over 2. So this implies that alpha is equal to minus b over 2. Yes, so this is my alpha. And then beta and gamma are both equal to 0. and then I have theta is equal to b over 2. Yes. So because minus theta is supposed to be minus b over 2, so this gives me that theta is equal to b over 2. So this means that finally the matrix Z that I was looking for has this form. Alpha is minus b over 2, beta and gamma are both equal to 0, and theta is equal to b over 2. Okay? Now I have another piece of information, and that is x times y times z is equal to I. Because all the matrices x, y, and z on the left-hand side are given to be 2 by 2 matrices, so the identity matrix on the right-hand side should also be a 2 by 2 matrix, because the product of 2 by 2 matrices on the left-hand side turns out to be a 2 by 2 matrix at the end. So now if I replace x, y, and z with the given matrices, I will have this. Yes. And then instead of z, I just plug what I got right now. This is supposed to be the identity matrix 2 by 2, so this is this matrix. But now on the left-hand side, I have the product of 3 matrices, but I know that the matrix multiplication is associative, so it doesn't matter if I multiply these two first and then multiply the answer to the third matrix. Okay, so I will multiply these two first. Okay, so this implies that the multiplication of the first two matrices is very simple, so it becomes minus b over 2. The first entry, the second entry, and the third entry are 0, and then finally the fourth entry becomes b over 2, and then I have to multiply it by the answer. So what you see here is the product of these two that I wrote here, and then I have to copy and paste this matrix next to it. So it becomes minus b over 2, 0, 0, b over 2, and I again put equate it with this identity matrix. And I have to do the product once more on the left hand side. So what I get is b squared over 4, the next one 0, the next one 0, and the next one again becomes b squared over 4. Yes, on the right hand side I have only 1, 0, 0, 1. So this gives me that b squared over 4 is actually equal to 1. So this means that b squared is equal to 4. So this means that b is equal to plus or minus 2. So that would be the answer that I am looking for. So this is the solution of this problem. Okay, problem C. Let A be this 3 by 3 matrix. Write A as a product of an upper triangular matrix by a lower triangular matrix such that the entries on the main diagonal of the upper triangular matrix are all equal to 1. Okay, so what we are supposed to do, we want to write this matrix, this 3 by 3 matrix, as a product of two triangular matrices. So upper triangular and lower triangular. Upper triangular on the left with entries on the main diagonal all equal to 1. So the entries below the main diagonal should be equal to 0, because this is going to be an upper triangular matrix, and other entries we don't know, so let me call them A, B, and C. I am supposed to multiply this by a lower triangular matrix, but we don't know about the entries, so let me call the entries D, E, and F. Because it is going to be lower triangular, it means that any entry above the main diagonal should be 0. But then the entries below I don't know, so F, G, H, I, let me call them for example. This product is going to give me the matrix A. So I want to find these lower triangular and these triangular matrices with these conditions, so that when I multiply them in this form, it gives me matrix A back. Okay, so what we can do, we can just multiply the left hand side. So if I multiply the first row by the first column, 1 will be multiplied by D, gives me a D, the next one will give me AG, the next one will give me AH, so I have to add them. D plus AG plus BH is the first entry. Then I go to the next one, it gives me AE plus BI for the obvious reasons that you already know about it. So then the last one would be only BF. Then I go to the second row. The second row gives me G plus CH, and then E plus CI, and finally CF. And then the last row will give me H, I, and F. This is going to be equal to this matrix that you see here. 1, minus 1, 2, minus 1, 5, 4, 2, 4, and 14. So this immediately, if I compare the last rows, it means that it becomes obvious that H should be equal to 2, I is equal to 4, and CF is equal to 14. Yes? So these are the numbers that I immediately get by comparing the final rows. But for example, now I can go here. This number should be equal to 4, but I already know F, so I can say that CF is supposed to be equal to 4, but F is already found to be 14, so 14C is equal to 4, and then this means that C is equal to 2 over 7, so that is also one of the entries that I was looking for. Then I go here, for example, it should be equal to 2, so BF is equal to 2, but I already know BF is 14 again, so 14F is equal to 2. So this gives me a 1 over 7. Sorry, B is 1 over 7. So that is also we know. Okay, now for example, you can go here. This entry should be equal to 5. So E plus CI should be equal to 5. What I know about C, I don't know E, plus, but I know C is 2 over 7, and I know that I is equal to 4. The answer should be equal to 5. So this means that C is equal to 5 minus 8 over 7, and if I simplify that, oh sorry, this is not C, this is E. E should be 5 minus 8 over 7. So this is 35 minus 8 is 27. So E is 27 over 7. So that is also the entry E. And now, for example, I can go to this entry G plus CH. So I have G plus CH is supposed to be equal to minus 1. But I don't know G. I know C, which is 2 over 7, and I know H, which is 2. The answer is supposed to be equal to minus 1. So G becomes minus 1 minus 4 over H, which is minus 11 over, sorry, minus 4 over 7, which becomes minus 11 over 7. So this means that G is minus 11 over 7. So this is also another entry that I was looking for. Now I can go here and compare these two, yes? So AE plus BI is supposed to be equal to minus 1. So what is A? We don't know yet. But do I know E? Yes, it is 27 over 7. Do I know B? Yes, it is 1 over 7. And I know that I is 4. The answer is supposed to be equal to minus 1. So this means that 27 over 7a is equal to minus 1 minus 4 over 7. So the answer becomes minus 11 over 7. So then if I simplify this 7 with that 7, so a becomes minus 11 over 27. Yes, so this is the value for a that I get. Okay. And then finally, I will start comparing this one with that one. So D plus AG plus BH is supposed to be equal to 1. So this implies that D plus, I know A is minus 11 over 27 multiplied by G, which is another minus 11 over 7 here, plus B is 1 over 7 and h is 2, this answer is supposed to be equal to 1. So let me do this a little bit long calculation here. So this becomes 1 minus 2 over 7. Okay, so if I multiply 11 by 11, 121, so I will move it to the right hand side, it becomes negative, and this becomes 189, yes? So then I need to simplify and calculate this. So the common denominator is 189, so this is 189, and this is 27 times, this becomes 54, and then I have minus 129. So this is 60, this becomes 6 over 189. But this can be simplified by 3, so this becomes 263. So this is also D. Now if I make it a little bit smaller so that I can read everything, so here finally I can say that my matrix A can be written as this product. 1, you see I am just plugging these numbers here. A is minus 11 over 27, and B is 1 over 7, 0, 1, and C is 2 over 7, and finally I have 0, 0, 1 multiplied by D, which is 2 over 63 and 2 zeros here, and G is minus 11 over 7, E is 27 over 7, 0, and HIF, which is 2, 4, 14. So it means that I was able to write A as the product of an upper triangular matrix with a lower triangular matrix. We will talk about this later. This is called LU decomposition, but of course LU, L stands for lower, U stands for upper. In principle, I should write the lower triangular matrix on the left hand side and the upper triangular matrix on the right hand side to have LU decomposition, but here I have UL decomposition if you want to have the name. I will talk about this a little bit later. Okay, well, now we go to the next problem. Sorry, I think I made a mistake here, because if you see this number is 121, I wrote 129. Let me clean this. So this is 121 now. So if I subtract 121, this becomes 68, and then it becomes 14, not 6. So this becomes 14, and now if I divide by 7, so D becomes 2 in the numerator and 27 in the denominator. Okay, sorry, that was my bad. Okay, and then if D is this number, where is D happening? D is here, so I need to clean this one as well and write 2 over 27. Okay, now this is the correct answer. Sorry. Okay, problem D. Let A and B be matrices so that AB is defined. Describe how A times B, this product, will alter if the ith and jth row of A are interchanged. S times of each entry on the jth row of A is added to the corresponding entry on the ith row of A. Number 3, the ith and jth columns of B are interchanged. Number 4, S times of each entry on the jth column of B is added to the corresponding entry on the ith column of B. Okay, I would solve only part 2 of this problem. Solving other parts are completely similar. So, what does this question mean? So let us consider that this A that I am working with is an m by n matrix for definiteness of the discussion. Okay, and let, for example, I be an integer greater than or equal to 1 and less than j, and j itself is also less than or equal to m. So from this m by n matrix, right now I am concentrating on two rows, number I and number j. Of course, here I have assumed that I is less than j. It hasn't been mentioned in the problem itself that which one is smaller than this one, but there is nothing serious actually about this order. You can follow what I'm going to tell you for the other case that j is smaller than I. So I do not lose any generality by assuming that I is less than j here. Okay, so if you want to imagine this matrix A is an m by n matrix. So let me write, for example, the entries on the first row is A11, A12, and then A1n. And then I continue until I reach to the ith row, so it just becomes I1. The next one is I2, and it continues to AIN. And then I continue until I reach to the jth row, so it becomes IJ1, IJ2, AJ2, and then I will reach to AJN, and then I will continue until the very last row, which is A sub MI, sub M1, and A sub M2 until A sub Mn. So now what is happening? This tells you that you take this matrix and you multiply it on another matrix from the left, you get this product AB. Now what we do, we change this matrix a little bit. How? We keep everything the same unless we multiply the entries on the jth row by a number s. So this will give me s aj1, s aj2 up to s ajn, and then I add these numbers to this. But let me tell you something, I am not changing this. So in my head I multiply these numbers by s, and when I got their results I add them correspondingly to these entries. Okay, so in principle I am not changing anything except the ith row. So what I mean is that assume this the first row remains the same, the second row remains the same, but the ith row turns into this. It becomes AI1 plus s times AJ1. The second one becomes AI2 plus s AJ2, and then it continues, you reach to this AIN plus SAJN. This would be the second row, this would be the ith row, any row, even the jth row remains the same. This is what we mean in this problem. Yes, and you continue, the last row also remains the same. Yes. Let me call this matrix matrix A prime. Now I multiply matrix A prime by the same matrix B. I want to see what would be the effect of this change in matrix A, how this change in matrix A will affect the product. The claim is that all the rows of matrix A prime B is the same as the rows of the original product AB except for the ith row, and the same thing that happened to the ith row of matrix A will happen to this product as well. Okay? So in principle, if I ask you what are the rows of matrix A prime, you will answer in this way. So let K be an integer between 1 and m. Okay, so if I ask you what is the kth row of matrix A prime, you would answer that if this k is not equal to I, it means that if I am talking about any row except the ith row, nothing has changed in this matrix, so it becomes equal to the kth row of the original matrix A. But if I ask you what happens if this k is equal to I, then you would say that the ith row of this matrix is the ith row of the original matrix plus s times the jth row of the original matrix if k is equal to I. Yes, so this is written everything the same thing in summary, yes, in a summarized form. Now my claim is that the same thing will happen for this product. So what does it mean? It means that I want to show that the kth row of A prime B is equal to the kth row of AB if k is not equal to I. So this is what I want to show. Another thing that I want to show is that the ith row of this matrix is equal to the ith row of AB plus s times the jth row of AB. This is also what I want to show. Okay, but they are very simple. So if you remember in the lecture, I told you how to find the kth row of a product. Okay, so here I should take the kth row of the matrix sitting on the left and multiply it by the matrix B as the whole matrix B. Yes? But now here I am solving this problem under this condition that k is not equal to I. But when k is not equal to I, there is no difference between r sub k of A prime and r sub k of A. So instead of r sub k of A prime, I just simply write r sub k of A multiplied by the whole matrix B. Another way of writing this is to tell the kth row of the product. So I am done. If k is not equal to I showed that the kth row of this new product matches exactly with the kth row of the old product AB. But now let us concentrate on the second one. What happens if I want to calculate the ith row of this product? Again, because I want to calculate the ith row of a product, I will take the ith row of the matrix sitting on the left and I multiply it by the whole matrix B. But now for the ith row, you see, if k is equal to I, so this means Ri A prime is equal to this. So instead of r sub I A prime, I can replace this expression. So this becomes Ria plus S Rja, and then I multiply it by the whole matrix B. But I know that matrix multiplication is distributive over the matrix addition. Okay, so I multiply it, so it becomes Ria multiplied by B, but I have to keep the order the same, so B should be multiplied from the right, and then S times Rja times B. But again, the first term can be written as the ith row of the product AB plus S. The second product can be written as the jth row of the product AB. And I am done. I wanted to show that the equality of these two, so I started from the left hand side and I showed that this is equal to the right hand side. So it means that exactly the same change that I have applied for matrix A to get matrix A prime will transfer to the product itself. Yes, so the product will also go under the same change that A has gone. Okay, that is also similar for other parts, but of course you need to use other relations. So you know, for example, that if I want to talk about columns, I have a formula that the kth column of the product is equal to the whole matrix A multiplied by the kth column of matrix B, the matrix sitting on the right. So that would be useful information for the other parts, the part 3 and part 4. Okay, now we go to the next problem. We go to problem E. Let A and B be matrices such that the sum of entries on each row of A is the same for all rows of A, and the sum of the entries on each row of B is the same for all rows of B. Prove that if AB is defined, it enjoys the same property as A and B do. Okay, so how should we solve this problem? For definiteness of the discussion, let me have A as an m by n matrix and B as an n by p matrix. Then of course it would be clear that the product AB is an m by p matrix, yes? We also know that the sum of all the rows of the matrix A are the same number. So let me call it SA. So SA, the sum of entries on each row of A. This has been claimed by the problem itself. A has this property that the sum of entries on each row is the same for all rows. And let me call that number SA. Similarly, let me call SB the same thing. So the sum of entries on each row of matrix B. Now we claim that this product, the sum of entries on each row of this product is also is the same for each row. Okay, to prove this, I could take a row from this matrix. Because this matrix AB is an m by p matrix, I would say that let I be an integer between 1 and m. Okay, the elements of the entries on the ith row of this matrix are these numbers, yes? So AB I number 1. This is the first entry on the ith row of this product. Then the next one is AB I2. This is the second entry on the same ith row of this product. How many entries do we have? Because this matrix is an m by p matrix, I can continue this list until AB IP. Yes? And then I want to add them. And the claim is that this sum is always the same regardless of the value of I that you choose in this interval. Okay? So it would be easier if I write this sum as a sigma. So I would write this as a sigma AB. Then I will have IJ. I is fixed, by j runs from 1 up to p. But then this can be written as, let me copy and paste the sigma here, but we have a formula for the ijth entry of a product. This is equal to a sigma. I need to choose a counter for my sigma. Let me call it k. It goes from 1 up to the number of columns, or equivalently to the number of rows of matrix B. So this becomes up to n, and then I will have A ik multiplied by bkj. But we know that if we have two finite sums, I can interchange the sums. So I can write the sum of k from 1 to n, then sigma j goes from 1 to p. Then I will have that product. But now look here. The counter of this sigma is j, and this entry is independent of the counter of the sigma. It only depends on I and k. So as far as this sum is concerned, I can pull this out. Yes? So then this becomes sigma, k goes from 1 to n, and then I will have a sub ik, and then I have a sum of b sub kj, and j goes from 1 to p. Now if I ask you what is this sum, you would say that this is the sum of all entries on the kth row of matrix B. So these are the entries on the kth row of matrix B, and I am considering all of them from the first column to the pth column. So the sum is SB according to what we assumed in the problem. So this sum can be written as SB. So then this becomes sum, k goes from 1 to n, and then I will have a sub ik multiplied by SB. Yes? But this SB is a constant, so I can pull it out from this sigma. Then it becomes from k to n, and then I will have a sub ik. Now if I ask you what is this one, these are the entries on the ith row of matrix A. K goes from 1 to n, so I am adding all the entries on the ith row. But according to the assumption, this number is SA. So this becomes SB times SA. So I showed that if the sum of the entries on each row of matrix A is a constant number, say S sub A, and if the sum of entries on each row of matrix B is the constant number S sub B, then the product has the same property, namely that the sum of entries on each row of the product is a constant. We not only proved that, but we also proved that that constant is the multiplication of these two constants. Okay? Now we go to the next problem. Okay, problem F now. Let B be a matrix that commutes with a diagonal matrix with no entries equal to each other. Show that B is a diagonal matrix. Okay, so let me take my diagonal matrix of this form. So the diagonal matrix claimed in the problem is of this form. Say D1, D2, up to say it's ordered n by n, and then everything here is 0. So if I ask you what is for example the st entry, so s is an integer between 1 and n, let us say, and t is another integer between 1 and n again. If I ask you what is the entry on the s row and tth column, you would say this is on the th row, so it becomes ds, and then you have delta st. This is the Kronecker delta, yes? Because it is clear that if s is not equal to t, then definitely this becomes 0, and that is correct. This should be equal to 0. And if s is equal to t, then this is 1, and this is of course ds, and that's correct. Okay, now what we want to show, assume that this matrix B commutes with matrix D. So we know that this BD is equal to DB. By the way, we know that none of the entries on the diagonal of this diagonal matrix are equal. So it means that so all of these numbers that you see here are different. Okay, so I want to show that B is also a diagonal matrix. So I would say that let I be an integer between 1 and n, j be an integer. Of course, if these two matrices are commutative, it means that B is also an n by n matrix, yes? So j is also between 1 and n. So let me take I, an integer between 1 and n, j, an integer between 1 and m. We show that the ijth entry of B is 0 if I is not equal to J. This is what we want to show. Okay, so we know that because BD is equal to DB, therefore the ijth entry of this matrix is also equal to the ijth entry of this matrix. Yes, but the left hand side can be written as a sum of the ikth entry of B, a kjth entry of D, k goes from 1 to n. This should be equal to sigma. Again, I can write k goes from 1 to n. This time I can write D I kth entry and then B k jth entry. Let me write everything with lowercase letters. It is easier, so it becomes B I k D k j. K goes from 1 to n, and then you have sigma. K goes from 1 to n. You have D I k and B k j. But then what can I write? Instead of dkj, I can use this rule and write sigma k goes from 1 to n bik multiplied by, instead of dkj, I can write dk delta kj. Yes? So here what I have done, instead of s in this formula, I have written k, and instead of t I have written j, and this is the thing that we get. Similarly, I can do the same thing on the right hand side. Instead of dik, I can write di delta ik, and then I have bkj. But on the left hand side, from the properties of the Kronecker delta, I can use this Kronecker delta to eliminate the sum with the counter k, provided that I replace k everywhere left with the second index here. So this becomes bij, and then I will have dj is equal. I can do the same thing on the right hand side. I can use this delta to eliminate this sigma, provided that I replace k with I everywhere left. So what I have on the right is di, and then this becomes bij. And now I move this to the left hand side and factor bij out, so it becomes bij dj minus di is equal to 0. So either this one is equal to 0 or that one is equal to 0. But that one is not equal to 0 because I assume that all of these numbers are distinct. So then this implies that bij is equal to 0, and that is what I was looking for to prove. Yes? Okay, now we go to the next problem. Okay, now problem G. Let A be a square matrix of order n such that the commutator of A and B is equal to the 0 matrix for all square matrices B of order n. Show that A is a scalar matrix. Okay. So let me write this sentence. We know that this commutator is equal to 0 for all possible n by n matrices B. So we know that for all matrices n by n matrices B, we know that A and B equals to the 0 matrix. Now what I say is that let us consider this very particular diagonal matrix. 1 n by n, 2, 3 up to n, and everywhere else equal to 0. Yes, so this is an n by n matrix, and I know that this matrix A commutes with all n by n matrices, including this particular matrix D. So it means that I can conclude that A commutes with this D that I have defined in this particular way, and now I will invoke the previous problem F. So you see this problem here, of course here if I give this the name A, if I know that this matrix, I have a matrix which commutes with a diagonal matrix with no equal entries, then that matrix itself has to be a diagonal matrix. Okay? So here I know that I have a matrix because this matrix commutes with all n by n matrices, it also commutes with this particular n by n diagonal matrix. But the entries on this diagonal matrix are not equal, none of them. So based on problem part F, I can conclude that A is a diagonal matrix. Yes? But this is not enough because I want to show that A is a scalar, so I have to show that all entries on the main diagonal are equal. So how should I prove that? So I would say that let, for example, S be an integer between 1 and n, and let t be also an integer between 1 and n, and let us assume that S is not equal to t. We show that A tt is equal to A ss. So I'm trying to show that the element of matrix A on the tth row and on the tth column is equal to the element on the th row and th column are the same. I want to show that. Okay, the trick is that I would define another particular matrix. So I would say let E be an n by n matrix with entries little e sub ij, and I define E sub ij as this. I would say this is the delta with I and t, I and s, multiplied by delta of j and t. So you see, I am defining the entry on the ith row and jth column of this matrix in this way. This I is this I here, this S is that S that I fixed there, and this J and this J are the same, and this T is the number that I have already fixed. Anyway, this is an n by n matrix. Again, I know that my matrix A commutes with every n by n matrices, including this new matrix. So it means that A and E commute. So this means that AE is equal to EA. And if these two matrices are the same, the entry of this matrix on the left on the S row and tth column is equal to the corresponding entry of this matrix, yes? But now I can write the left hand side as a sum. The sum of little a sub sk e k t, k goes from 1 to n, and on the right hand side I can write another sum. This is, I have e here, I have a here, my e indices start with s and then ends with the counter of the sigma, say counter of sigma is again k, and then kt. Okay, but now let me replace what I know about the E entries, yes? So sigma k goes from 1 to n, ask, but what can I write instead of ekt? I use this relation, so I have two deltas. So I have delta and delta. The first index of delta is the row index of E, which is k. The second index is S. Second sigma, the first index is the J index, is the column index of E. The column index here is T. And then it ends with, and then it ends with a T. Yes? On the right hand side, I also have the same situation. So k goes from 1 to n. Again, what is ESK? So I have two deltas, a product of two deltas, and then I have A sub kt. How should I write the first delta? The first index I is the row index of my matrix A, so here is S. The second index of the first delta is the number S, so that is also S. And then when I go to the next delta, it starts with the column index of my E. Column index of my E is K, so I would write K. And it ends with T, so this becomes T. But this number, this delta is 1, this delta is also 1, so I can get rid of them. So it becomes sigma, K goes from 1 to N, A sub K sub Sk, delta Ks, and the right hand side I will have sigma, delta Kt, Akt, K goes from 1 to N. But this sigma can be used to eliminate this sigma, and then I have to replace K with S. So what is left on the left hand side is just simply ASS. And for the same reason, I use this delta to eliminate this K, this sigma, and then I will replace K with T. So it becomes, ATT. And that's what I wanted to show. So I proved that this should be a scalar matrix. If this property holds, it's inevitable. That matrix A has to be a scalar matrix. But to show that this is indeed true, I need to prove that really this is the case, that all scalar matrices, any scalar matrix that I have, commutes with all n by n matrices. Yes? So I would say that now let A, so I just want to show that this is indeed possible. This shows that if this condition holds for a given matrix, it's a logical conclusion that this matrix should be a scalar matrix. But now I want to really investigate that if the scalar matrix indeed commutes with any matrices, any 2 by 2 matrices, every 2 by 2 matrices. So let me write let A be a scalar matrix. Like this. So let me write a scalar matrix like this. I will have A up to A. So this means that any entry Aij is equal to A times delta Ij. Yes, this is the meaning of being a scalar matrix. Okay, then we know that this will commute. So by the way, this is very easy. I don't really need to prove that, because every scalar matrix, let me write this, let A be a scalar matrix, then A is actually A times I for some A belonging to R. Yes? So then it is clear that A times B for any B is AIB, and this becomes AI times B minus B times AI, and this becomes AB minus AB, and that is the zero matrix. So this is clear that if I have a scalar matrix, that scalar matrix actually commutes with every 2 by 2 matrices. And on the other hand, I show that if this is going to work for all n by n matrices A, n by n matrices B, then A has to be a scalar matrix. Okay, so we go to the next problem now. Okay, problem H. Determine all matrices B such that the commutator of A and B is equal to the zero matrix, where A is equal to this given 2 by 2 matrix. Okay, so here, because A is a 2 by 2 matrix, in order for this commutator to be defined, B has to be a 2 by 2 matrix as well. So I am looking for all those possible B matrices. So let B be equal to this given 2 by 2 matrix, A, B, C, D. Okay, because it is mentioned that the commutator A and B is equal to the zero matrix, I can conclude that AB is equal to BA. Then this means that the matrix 1, 1, 0, 1 multiplied by this matrix B, which is A, B, C, and D, is equal to the matrix B, which is A, B, C, D, and multiplied by 1, 1, 0, 1. I want to find a relation among these numbers so that those relations guarantee this equality to be true. Okay, so the left hand side, I just multiplied these two matrices. So it's very simple task now. So it becomes A plus C, the first one. The second one becomes B plus D. The next one becomes C, and the next one becomes D. Yes? This is the product on the left hand side, and the product on the right hand side can be done similarly. So it becomes A plus B, and then I have C, and then I have C plus D. So for these matrices to be equal, I have to guarantee these conditions. A plus C should be equal to A, B plus D should be equal to A plus B, and then C should be equal to C, and D should be equal to C plus D. But from the first relation, I immediately conclude that C has to be equal to 0. And from this equality, I can conclude that by canceling B, I will get that A has to be equal to D. Okay, so the third one doesn't give me any information. C is always equal to C. But from the last one, I can conclude by eliminating D, I will get C is equal to 0 again. Okay, so it means that I have two constraints only. One on C. C has to be equal to 0. And another constraint is that A should be equal to D. I don't have any constraints on B. So it means that the general form of my matrix B was A, B, C, D. But then this means that A is equal to this. So let me write A instead of B. I don't have any restrictions on B. So B is B, C has to be equal to 0, and D has to be equal to A. Yes? So it means that if I have a matrix of this form in which this off-diagonal entry is 0, this off-diagonal entry is an arbitrary number, and the entries on the main diagonal are equal, then I will have a matrix which is definitely a commuting matrix, a matrix that commutes with matrix A. Okay? Now let us solve another problem. Okay, let us solve the next problem, problem I. Let A, B, and C be square matrices, all of the same order, and let lambda be a number. Prove that. I want to prove these relations among different commutors. Okay, so the first one and the second one are very simple, so let me start with number 3. Okay, so number 3. I start from the left hand side. This becomes equal to A and the commutator of A and B plus C. According to the definition, I need to write the matrix on the left multiplied by the matrix on the right, and then write the other way around and subtract them. And then I know that matrix multiplication is distributive over the matrix addition, so I can write AB plus AC for the first one, and I can write minus BA minus CA for the second one. But then you see that I can collect them in this form. I can write AB minus BA together, and I can write AC minus CA together. But the content of the first pair of brackets is nothing except the commutator of A and B, and the same thing for the second pair of brackets. So that's the commutator of A and C. So then this becomes the right hand side. Yes? Okay. Of course, the same is true. I have written it for addition, but you can also write it for subtraction. Yes, so let me change my color. So if I have A and B minus C, it's clear that I can write it in this form: A, B plus minus C. And because now I just showed that this is valid for the addition, so I can write this plus A and minus C. But here, if you solve part 2, if I take my lambda equal to minus 1, this lambda can be pulled out. So this minus 1 can be pulled out, and then it becomes AB minus AC. So even though I have written it for addition, that's clear that it's also valid for subtraction. Okay, let us go to number 4. So number 4, I would prefer to start from the right hand side. So the right hand side, I have BAC plus AB multiplied by C. My goal is to show that if I have the commutator of a matrix with a product, I can write the commutator of the first matrix and the third one, and then I can pull B out, but I have to pull it from the left. And I can pull C out in the next term, but I have to pull it from the right. Pull it out from the right. Okay, so if I want to show that, I will start from the right hand side and then just simple calculation. Instead of commutator of A and C, I write the definition, which is AC minus CA. And for the commutator of A and B, I would write AB minus BA, just the definition, and then I have a C at the end. And I will start multiplying B inside, so it becomes BAC minus BCA, and then I will have ABC minus BAC. Yes? And then if you see here, this one and that one are cancelled, so I can write this as ABC. I can write it as, let me change my color. I can write it as ABC minus BCA. But you know that matrix multiplication is associative, so for the first product, I can assume that this is A times B and multiplied by C. And the same thing, I collect B and C together again, and then I multiply it by A. But now you see this is exactly the definition of the commutator of A and BC, which is exactly equal to the left-hand side. Okay? Okay, now let us go to number 5. Okay, I will start from the left-hand side and just use the definition of a commutator repeatedly, okay? So, number 5, so let me keep it in a way that we can see it. So this is number 5. So here, what I do is that first, I will write the definition of this internal commutator here, here, and here. Okay, so the left-hand side equals to, this becomes the commutator. The commutator of B and C is BC minus CB. And then after that, I will write the commutator of B. The commutator of C and A is CA minus AC. And then I have plus. I have C. The commutator of A and B is AB minus BA. Now, once more, I use the definition of a commutator in each one of these commutators individually. So this becomes the product of A to this one and minus the other way around. Yeah? So this becomes A multiplied by BC minus CB, and once more the other way around, BC minus CB multiplied by A, and then subtraction. What I have written here is the answer is actually equal to the first commutator. And I will do the same thing for the other ones. So this becomes B multiplied by CA minus AC minus CA minus AC multiplied by B. And the next one, plus C times AB minus BA, and then minus AB minus BA multiplied by C. And then I will distribute these matrices inside. So the first one, I need to be careful to keep the order exactly the same. So I multiply here from the left. So I have to write ABC minus ACB. I do this multiplication here and here, and then of course I have an extra negative sign. So the first term becomes minus BCA but positive CBA. It's extremely important to keep the order because you know that matrix multiplication is not commutative. And the next one is BCA minus BAC, and then I will have minus CAB plus ACB. The second line would be plus CAB minus CBA, and then finally minus ABC plus BAC. I'm just multiplying them normally, okay? And if everything is right, everything should cancel out. So let us see if it is the case. So you see here, this ABC positive minus ABC negative, they are canceled. So for example, you know that you're not allowed to cancel these two because they are not in general the same matrices. Yes, matrix multiplication is not commutative. Okay, a minus ACB, minus ACB, and then positive ACB. Yes, they are canceled. Minus BCA, positive BCA. Positive CBA, negative CBA. And negative BAC, positive BAC, and finally negative CAB and positive CAB. So all of them are cancelled, so what is left is the zero matrix, and it's exactly the right hand side. Okay, so now we go to the next problem. Okay, problem J. Let A, B, and C be square matrices all of the same order such that A commutes with both B and C. Show that A commutes with B times C as well. Okay, it's extremely simple problem. So what we know is that A commutes with, so I would say that A commutes with B. This means that the commutator of A and B is equal to the zero matrix. I also know that A commutes with C. Then this means that the commutator of A and C is also the zero matrix. Now I want to show that A commutes with the product. Okay, so it means that my goal is to show that A commutes with BC, so this means that I need to show that this is indeed the case. Okay, but now if we go back here, I can use this relation. Okay, I want to calculate the commutator of a matrix with a product, so I can use this rule that we proved in the previous problem. So I would say that, okay, A, B, and C is equal. I pull B out from the left, and then I have this commutator, and then I will pull C from the right, out from the right, yes, so it becomes AB times C. But now I know that the first commutator is 0, so I can put the 0 matrix here. This matrix is also 0, so I can put the 0 here. So it becomes B times the 0 matrix plus the 0 matrix times C. It is the 0 matrix plus the 0 matrix, and the answer is 0. Okay, now we go to the next problem. Okay, problem K. Given that x is equal to this expression and y is equal to this expression, we are supposed to prove that x can be expressed as this expression, where this numbers that you can see here satisfies this matrix multiplication relation. Okay, the first thing that I would do, I would say that, okay, this relation connects x to y, this relation connects y to z, but what I want to show is a connection between x and z. So the strategy is clear. I need to replace this y with this given expression. Then it is clear that I will connect x to z, and then I need to do some algebra then, okay? So let us do that. Okay, so I would say that x is equal to, my x is this one, so what I am doing, I am replacing this y here and there with this given expression. So what happens, it becomes a1 multiplied by b1z plus b2 divided by b3z plus b4, and then after that I have a2, And then below this I will do the same thing, yes, but I have A3 this time multiplied by the same expression. It's B1z plus B2 divided by B3z plus B4, and then after that you see that I have an A4 there. Okay, so to simplify this, I want to get rid of these partial fractions in the numerator and the denominator, so I rescale this big fraction by this denominator. So I multiply the numerator and the denominator by this expression. What I get is this. It becomes A1 times B1z plus B2, then I will have A2 times B3z plus B4, and in the denominator I will have A3 times B1z plus B2, and then I will have A4 B3z plus B4. Yes? Okay, now you see that I have my connection. I have the connection between x variable and the z variable, but I need to organize them. But here you see in the expression that I am going to prove, in the numerator I have z in only one place. Okay, but I have z here in two places. So if I multiply this and factor it out, then it becomes simple, yes? So this becomes equal. So I multiply A1 here, it becomes A1B1Z, and then I will have A2B3Z, and I factor that, z out. So it becomes A1B1 plus A2B3, and then I have Z. And then I will have A1B2 and A2B4 left. Yes. And then I do the same thing for the denominator. Then I will have A3B1 plus A4B3Z. And then I will have A3B2 plus A4B4. Yes? So this is what I prove. So if I compare this that I got with what I am supposed to get, I realize that if everything goes smoothly and fine, these numbers, this number here is C1, this number here is C2, this number here is C3, and this is finally C4. Okay, so comparing these two relations, I would say that C1 has to be equal to A1B1 plus A2B3, and then I will have a C2 A1B2 plus A2B4. C3 is equal to A3B1 plus A4B3, and finally C4 has to be equal to A3B2 plus A4B4. So it means that if these C's claimed in the problem are these numbers that I get here, then I have done everything correctly. But let us see, what guarantees that these are indeed the cases? Probably this relation. So let us see what is the meaning of that relation if I do the matrix multiplication and compare the entries of the matrix on the left with the entries of the matrix on the right. Okay, so here I would write it like this. So you see C1, C2, C3, C4 is equal to, I will do this product. So this product is simple to do. Yes, it becomes A1B1 plus A2B3. The next one is A1B2 plus A2B4. The next one is A3B1 plus A4B3. And the next one is A3B2 plus A4B4. Yes? So then this exactly gives me these relations, yes? Because C1 has to be equal to this, and yes, we also got the same. C2 has to be equal to this expression, we also got that one. C3 has to be equal to this, we also got that. And finally C4 has to be equal to this, and we also got the same thing. Yes? So that is actually the end of the solution to this problem. Now let us go to the next problem. Okay, problem L. Matrices sigma 1, sigma 2, and sigma 3 defined in this way, where I is the imaginary unit, occur in quantum mechanics and are called Pauli matrices. Show that for all I and j belonging to the set 1, 2, 3, the commutator of sigma I and sigma j is equal to 2 times I, the imaginary unit, the sum over k epsilon ijk sigma k, where k goes from 1 to 3, where epsilon sub ijk, called the Levi-Civita symbol, is defined by this rule. Okay, I would say that this is an exercise in reading the notation more than being an exercise in matrix multiplication. Okay, so how should we do that? We want to prove this equality for all possible choices of I and j in this set. So I is 1, 2, 3, and j is also can take values 1, 2, 3. So in principle, I have 3 times 3, 9 situations to prove. Yes, I need to consider 9 cases. Okay, so what are the 9 cases? So I can consider sigma 1 and sigma 1. I can consider sigma 2 and sigma 2, the commutator of sigma 3 and sigma 3. And then, of course, I have sigma 1 and sigma 2, and for the sigma 2 and sigma 1, and the same as sigma 2, sigma 3, sigma 3, sigma 2, and then a sigma 3, sigma 1, and sigma 1, sigma 3. Yes, these are the 9 cases that in principle I should consider. But of course, the commutator of every matrix with itself is the zero matrix. So this is the zero matrix, this is the zero matrix, this is the zero matrix. So I need to confirm that for these cases, the right-hand side is also the zero matrix. For example, let us just consider one of them from all these 3. Let me consider the first one. Okay, so I need to convince myself that sigma 1, the commutator of sigma 1 and sigma 1 is equal to, so I am taking I to be 1, I am taking j to be 1 again. So I need to convince myself that this is 2 times I, the imaginary unit, sigma k goes from 1 to 3, epsilon 1, 1, and k sigma k. This is the relation that I need to convince myself of. Yes. Okay, here the left-hand side is actually the commutator of sigma 1, sigma 1, but of course this means sigma 1, sigma 1 minus again sigma 1, sigma 1, which is the zero matrix. What is the right-hand side? The right-hand side is 2i, the imaginary unit. Let me just expand this sigma. Of course, we really don't need to expand this sigma, because let me just calculate epsilon 1, 1k. Okay, so if I calculate epsilon 1, 1k using the given definition, this becomes 1 over 2. I is 1, j is also 1. And j is 1, k is any number from 1 to 3, let us keep it, and then again k minus 1, because I is 1. But here actually I don't care what the value of k is, because 1 minus 1 is 0, so this epsilon 1, 1k is always 0. So the right-hand side becomes also 2i times k goes from 1 to 3, 0 all the time, times sigma k, which also is equal to 0. So that this means that the left-hand side is actually equal to the right-hand side. Immediately you can convince yourself for this one and for that one. For the other ones, I need to consider only these 3, yes? Because calculating this is just multiplying the first one by a negative sign. So we know that sigma 2, sigma 1 is related to sigma 1, sigma 2 by this relation. That's only the minus sign difference. Okay, so let us, for example, consider one of these cases. Okay, so let me, for example, consider this first one, sigma 1, sigma 2. So I need to convince myself that sigma 1, the commutator of sigma 1, sigma 2, is equal to 2 times the imaginary unit I. Sigma k goes from 1 to 3, epsilon I j k. I is 1, j is 2 in this case, and k is just k, and then I have sigma k. Okay, so what I need to do, I need to calculate the left-hand side. When I calculate the left-hand side, it is sigma 1, sigma 2, the commutator, which is defined to be sigma 1, sigma 2 minus sigma 2, sigma 1. Okay, but sigma 1 and sigma 2 are given to me in the problem. This is sigma 1, this is sigma 2, so I just replace them. Sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I, 0. And then minus the other way around, 0 minus I, 0. And then I have 0, 1, 1, 0. I need to calculate these numbers, these matrices now. So the first one becomes I by multiplication, the second one 0, the third one also 0, and the last one minus I. Minus, if I multiply the other two matrices, it becomes minus I here, 0 here, 0 here, and I here. Now if I subtract them, I will have I minus minus I, which is 2I. The other one is 0, the other one is also 0, and then I will have minus 2I. Yes? So if I factor 2I out, then I will get 1, 0, 0 minus 1. Yes? And if you look here, this is the sigma 3 matrix. Yes? This is sigma 3. So this matrix is nothing except sigma 3. So this becomes 2I, the imaginary unit, multiplied by sigma 3. Now let me calculate the right-hand side. What is the right-hand side? The right-hand side is 2I, sigma, k goes from 1 to 3, epsilon I j k. But I is 1, j is 2, k is just simply k. And then I have sigma k. Now I expand this sigma. So this becomes 2I. It becomes epsilon 1, 2, 1, sigma 1, plus epsilon 1, 2, 2, sigma 2, and finally epsilon 1, 2, 3, sigma 3. Now here is my definition of Levi-Civita symbol. So what is epsilon 1, 2, 1? Here, I is equal to k is equal to 1, yes? So if I is equal to k, the last factor becomes 0, so the whole epsilon symbol becomes 0. So this is nothing except 0. The same is true for this one. Why? Because now j is 2, k is 2, so j and k are equal. So when j and k are equal, this middle factor is equal to 0, and then this means that this epsilon vanishes again. But what happens for this one, we have to calculate. So let me change my color here. Okay, so epsilon 1, 2, 3 is 1/2 I minus j. I is 1 in this case, j is 2, so it becomes 1 minus 2. Multiplied by j minus k. J is 2, k is 3 in this case. And finally, k minus I. K is 3, and then I is 1. Yes? So if I calculate this, you will see that this becomes negative 1, this becomes negative 1, and then this becomes positive 2. So if you multiply that, it becomes 1. So it means that the last epsilon is actually 1. And what you get is equal to 2I multiplied by sigma 3. But then if you compare this one and this one, you see that the left-hand side is exactly equal to the right-hand side. You can immediately convince yourself of other cases, but this is very simple. Exactly, the calculations are exactly similar to this case. Okay, now we go to the next problem. Okay, problem M. Let A and B be square matrices of the same order. The anti-commutator of A and B is denoted by curly brackets A and B, curly brackets closed, and it is defined by this is equal to AB plus BA. So the commutator of A and B is defined to be AB minus BA, but anti-commutator is defined to be AB plus BA. For the Pauli matrices defined in the previous problem, show that this is the case. Of course, this I is the 2 by 2 identity matrix. So that's more or less the same thing, okay? So let me just write the Pauli matrices here for you. So sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I, 0. And finally, sigma 3 is 1, 0, 0, minus 1. Okay? So if I want to show this, again, in principle, I should consider 9 cases, but in the case of the anti-commutator, it's clearly the case that the anti-commutator of A and B and the anti-commutator of B and A, they are exactly the same because we have here the addition of them. So in principle, I only need to consider 6 cases. Yes, so the cases that I need to consider is sigma 1 with sigma 1. I can consider sigma 2 with sigma 2, the anti-commutator of sigma 3 and sigma 3, and then anti-commutator of sigma 1 and sigma 2, anti-commutator of sigma 2 and sigma 3, and finally anti-commutator of sigma 1 and sigma 3. I really don't need to consider anything more. Let me just choose 2 of them. For example, let us this time consider this one and, for example, the last one here. Okay. So I need to prove that sigma 2 is equal to 2 times delta. Here I is 2, j is 2, so this becomes delta 2, 2, the identity matrix. This is something that I need to check. Okay. The left-hand side is equal to the anti-commutator of sigma 2, which becomes sigma 2 times sigma 2 plus sigma 2 times sigma 2. So what is sigma 2 is 0 minus I. So by the way, this, let me just make it simpler because they are exactly the same. So it becomes 2 times sigma 2, yes? And then this becomes 2 times sigma 2 is 0 minus I, 0, multiplied by sigma 2, which is 0 minus I, 0. And when I multiply them, it becomes 2. If you multiply this row by that column, so 0 times 0 gives you 0, minus I times I gives you minus I squared. But minus I squared is positive 1, and if you add 0 and positive 1, it becomes 1. And then you can continue. For the next one, it is 0. For the next one, again, it is 0. But for the last one, again, for the same reason, it becomes 1. And if you see, this is exactly equal to 2 times the identity matrix. Okay, but on the other hand, because delta 2, 2 is also 1, so the right-hand side is also 2 times I. So this is exactly equal to the right-hand side. For the last one, let us check the last one as well. Others are exactly similar. So sigma 1, sigma 3. What I need to, sorry, this is curly brackets. So this becomes sigma 1, sigma 2, sigma 1, sigma 3, plus sigma 3, sigma 1. So sigma 1 is 0, 1, 1, 0, multiplied by sigma 3 is 1, 0, 0, minus 1, plus sigma 3 is again 1, 0, 0, minus 1, multiplied by sigma 1, which is 0, 1, 1, 0. Okay? So now I start multiplying. The first multiplication gives me 0 here, minus 1 here, 1 here, and 0 here. And then when I add that one, so the second matrix becomes 0, 1, minus 1, and 0. And when I add them, it becomes 0, 0, 0, and 0. So this is the 0 matrix. Of course, it should also be the zero matrix because here I and j are different. Yes, I is 1, j is 3, so delta 1 3 is indeed 0, and 0 multiplied by the identity matrix is the zero matrix, so that's exactly equal to 2 times delta 1 3 I. Yes, so that's also very simple. Okay, so we were able to show that the left-hand side is equal to the right-hand side for these choices of I and j. You can similarly prove the other cases yourself. Okay, let's go to the next problem now. Okay, problem N. Square matrices A and B of the same order are said to anti-commute if their anti-commutator is the zero matrix. Show that any pair of the following matrices which occur in quantum field theory and are called gamma matrices anti-commute. Of course, here I mean that pair of distinct elements of these two matrices. That's also a very simple problem, but you need to consider case-by-case scenario here again. So, for example, let us consider the first matrix and the second one. We want to show that these two matrices, these two gamma matrices, which occur in quantum field theory, they anti-commute. So what does it mean? It means that the anti-commutator should be equal to the zero matrix. And that's just a simple matrix multiplication. So first let me just write the definition of the anti-commutator for this pair of matrices. This becomes gamma 1 times gamma 2 plus gamma 2 times gamma 1. So, but what is this one? Gamma 1 is a 4 by 4 square matrix here, defined in the problem. I just quickly write that. And then I multiply it by gamma 2, which is also another 2 by 2, 4 by 4 matrix. Of course, here I is also the imaginary unit. Okay, and then I add the other way around. I add this multiplication in the other way around. So 0, 0 minus I, 0, 0, I, 0. Yes, and then multiply it by this. Okay, I need to calculate two products here. So what is the first product? I know that I need to take decompose this matrix into rows and this matrix into columns and then multiply each row by each column. But this is a very simple task, so let me do it very quickly. The first row by the first column gives me minus I at the end, but all of the coming ones are actually 0. And for the second row, the first one is 0, the second one, the first one is 0, the second one is I, the third one and the fourth are 0. And when I go to the third one here, this is 0, this becomes 0 again, and then this becomes 0, and then this becomes 0 again. The last one gives me 0, 0, 0, and positive I. There should be some mistake somewhere. Let me double check. So I multiply this by that. It gives me that one is correct. So every one of them is 0. When I go to the second row, this turns out to be 0. The second one would be I. The third one 0. The fourth one also 0. When I go to the third one, this becomes minus, yeah, that is 0, 0. Yes, as I told you, the third one is wrong, so it becomes minus I here. Sorry. So this is minus I. Okay, and then I will do the other one. So this one by that one gives me positive I, and then the next one 0, the next one 0, the next one 0, 0, minus I, 0, 0, and here I will get 0, 0, I, and then I will also get 0, and this one gives me 0, 0, 0, minus I. Now I have to add them. When I add them, so you see that this one will cancel that one, this one will cancel this one will cancel this one, and finally this one will cancel this one. So I will get 0, 0, 0 everywhere. Yes? And that is the zero matrix. So I was able to show that these two matrices anti-commute. You can show this for gamma 1 and gamma 3, and you should also show this for gamma 2 and gamma 3. But that would be exactly the case. Okay? Now we go to the next problem. Finally, the last problem. Let A, B, C, and D be square matrices all of the same order. Show the following equality. Here on the left hand side we have the commutator of this product and that product. On the right hand side we have a combination of anti-commutators. Okay, so we learned that if I have two matrices x and y, the commutator of x and y is defined as x times y minus y times x. Anti-commutator of x and y is defined to be xy plus yx. These are defined in the previous problems. Okay, so I think it would be easier to start from the right hand side in this case, yes? So the right hand side is equal to, I have minus AC, instead of the anti-commutator of D and B, I write its definition, so it becomes DB plus BD. The same for others, yes, I'll just write the definition. So this becomes CB plus BC multiplied by D minus C, and then I will have DA plus AD times B, and finally I will have CA plus AC, and then I have DB. And then I use this distribution over addition, distribution of multiplication over addition. This becomes minus ACDB minus ACBD. I am not allowed to interchange any two matrices at all. So here, for example, if I want to multiply, I need to respect the order. A should be multiplied from the left and D should be multiplied from the right. So this gives me ACBD. The next one would be ABCD. And the next one, the same story, so it becomes minus CD, because I have also an extra negative sign. It becomes minus CDAB and minus CADB. And then I will have CADB plus ACDB. So let us see which terms are going to be cancelled now. Okay. So I have minus ACDB. Yes. So, okay, first of all, you see, I immediately see that these two are cancelled. ACBD, ACBD, positive, negative. And then what about this one here? You see this one at the end will cancel this one. Minus ACDB, positive ACDB. So they are also cancelled. Two more should be cancelled, yes? Which are these two, yes? Minus CADB, positive CADB. So these are left for me, but let me collect them using associativity. I can write it as AB multiplied CD. What I am writing here is this expression, and then I will have minus CD times AB. Yes, and that is exactly the definition of the commutator of AB with CD. Yes. The commutator is the matrix on the left multiplied by the matrix on the right, which gives me the first term minus the other way around. And that is exactly the left-hand side. Okay, thanks for watching. I hope that this video was useful for you. These are the references that I have used for making these exercises. Until the next video, be safe and goodbye.